Welcome back to P2. Today we're looking at methods of proof, Unit 1.6. Now, there are quite a few different ways in which you can prove something. For P2, we're going to concentrate on proving things by exhaustion or counterexample. When you get to P4, we'll also be looking at proof by contradiction. So, proof by exhaustion is kind of how it sounds. You exhaust every possible scenario. You break the problem down into smaller pieces and prove each individual one is true and separately, and thereby proving the whole statement true. This kind of method, it's only really useful when you're dealing with small sets of results, things that you can break down and actually look at every possible scenario. It's not really useful for when every scenario is actually going to be very time consuming. So it's for much smaller problems. For example, say I said prove that every odd integer between 2 and 16 is either a prime or a product of two primes. Well, that kind of statement you can break in, there's only a small number of odd integers between 2 and 16. So it's far easier to look at each one individually and prove it rather than try and come up with another algebraic method. Now, the second method of proof that we're looking at is counterexample. And this is essentially when you are finding an example to disprove something. For example, prove that the sum of two consecutive prime numbers is always even, or prove that this isn't true. And all you have to do is find one example that disproves it. You don't have to find lots of different things, just one counterexample that will disprove the statement. It's nice and easy. So let's have a look at a few examples. Okay, this example here is prove that the sum of two consecutive square numbers from 1 squared to 8 squared is an odd number. So this is one where I want to go with the exhaustive route. There's only a limited number of numbers, of combinations that I can have. They have to be consecutive square numbers. So 1 squared plus 2 squared, 2 squared plus 3 squared, and so on. So now we can see this is going to be 1 plus 4 is 5, 4 plus 9, 13. I'll fill the rest in. Now, as you can see, the statement is true, so it's always nice just to finish it off with, therefore, the statement is true, or something along those lines. Now, I've got a proof here that for all real values of x plus 6 all squared is greater than or equal to 2x plus 11. Now, it's very tempting to start with my statement here, but you should always start your proof from a known fact and not from your statement. So what's a good way of starting this? Well, what I'd like to do is have essentially a bit of jotting down the side of your work. Okay, so just in pencil down the side of your page, you want to start with a little bit of jotting, and what you do is that is where you start with your statement and play around with it. So I'm going to expand this and start to simplify it. And now I've got something to start with. This is where I want to start, because this now is a true statement. It's a statement of a known fact. X plus 5 all squared is greater than or equal to 0, because anything squared is greater than or equal to 0. So that is where I want to start my proof. So I'm going to start with this x plus 5 squared is greater than or equal to 0. And you want to start with just something like consider or let, just something along those lines as you get into it. So maybe if I start this again, a better way would be consider x plus 5 squared. And anything squared is greater than or equal to 0. And if you want to, you can put that in there somewhere. It isn't necessary, but you can. And from this point, what you want to be doing now is essentially working backwards through your jotting. So, my next step is to expand my bracket. And then I've got 2 more steps. So my next step after this will be to add the 2x to both sides. Then you can add your 11 to both sides. And then you can refactorize. Apologies. And something along those lines. Now, in some cases, not so much here, if it gives you something within the question, you should try and work out where that is relevant. So if it says like x is always positive, you have to use that within your proof. We've got all real values of x. That's kind of already given within this part of the statement. Okay, so I could have put here anything squared is greater than or equal to 0 for all real values. So I could have added to this bit for all real values. And that just includes then the statement within my proof. So we've got now, prove the following statement is not true. 2n squared minus 6n plus 1 is positive for all values of n. So all I need to do is find a value of n where 2n squared minus 6n plus 1 is not a positive number. So we're looking for it to be a negative answer. So if I think about this logically, if I put in a negative number, that's going to make this positive. Quite a large positive, this will be positive. So negative number is not going to do. And the larger the positive number I put in, the n squared will start to take over. So I want a small positive number. So what I'd like to start with is just substituting in n equals 1. So if I substitute n equals 1, 2 lots of 1 squared minus 6 lots of 1 plus 1. And that's going to equal 2 minus 6 plus 1, which is negative 3. So when n equals 1, 2n squared minus 6n plus 1 is negative. So the statement is not true. And that's an example how a counter example works. I'm just going to give you a couple of these to try, and as always the answers will be at the end. So for A here, we're just looking for one counter example. So one prime number that this doesn't work. So just looking at it, if I think of, say, let p equal 7, that's a prime number. 2 lots of 7 plus 1 is going to give me 15 which is not prime. And then of course I would just finish with, therefore the statement is not true. But I'm not going to write that bit after each one here, but that's what you should be doing, especially for any kind of exams, etc. If n squared is a multiple of 9, then so is n. So first we want to find a multiple of 9, and the easiest one to think about is one that's going to be a square number here. So as we're looking at n squared. So a multiple of 9 that's also a square number, let's go with 36. So if n squared is equal to 36, is a multiple of 9, then so is n. N in this case would be 6, and this is not a multiple of 9. Therefore the statement's incorrect. C, 5x is greater than 4x. This is going to be true for all positive values of x, but it's not going to be true for negative values of x. So if I start with, say, let x equals -2, then I can see that 5 lots of -2, is it going to be greater than 4 lots of -2? Well, obviously not. Okay, this statement doesn't work. Statement is incorrect. Therefore, the original statement is not true. So therefore, my 5x greater than 4x is untrue. I do apologise about my handwriting. If you've been following me, you know that my last iPad died and I've got a new one. And I had a paper screen on my other one, so on this one I'm finding it a little bit harder to write. So my writing's not great at the moment. Let me know in the comments if you are struggling with some of my writing today. Now, part D, you want to think of a value of x that this statement isn't going to be true. Well, it's going to be true for all positive x's, isn't it? Like 3 squared is 9, square rooted is also 3, think of it that way. But if I think, say, let x equals -3, then I can think of -3 squared and then square rooted. So square root of 9, which is 3, which does not equal x. Remember that if I was square rooted 9, I could obviously get a -3, but we're just using one example to show that this statement isn't always true. And then E, all odd numbers between 2 and 14 are prime. Well, 9 is odd between 2 and 14 and not prime. Again, don't forget to say at the end that your statement is false or that you've disproved the statement. Okay? Now, for this one, if we're talking about even numbers, all even numbers are multiples of 2. So if I think of 2 even numbers, we just want to say, well, let's start with let m and n be any 2 numbers. Therefore, 2m and 2n are even numbers. And that's my first bit, and this is going from a known fact. Multiples of 2 are even numbers. Now, we're looking for the product of them. So 2m times 2n is equal to 4mn. And we want to prove that this is even. So that equals 2 lots of 2mn. Okay, and that is my proof now. So I can then say as a statement, and there we have it. Just thought it was easier to write it down. Pause if you want to have a read here. Now, if I'm thinking of an odd number, okay, so if n is odd, so let's go with let n equal 2m plus 1. And the reason I do this is that 2 times something, so there's 2m part, is even. Okay, multiple of 2 is always even. A multiple of 2 plus 1 is therefore always odd. Okay, so that's my statement of fact that I have to start with, something that is a statement of fact. Now, if that's odd, let's look at n squared, would be 2m plus 1 squared. So it's going to be 4m squared plus 4m plus 1. And what I can do here is I can take a factor of 2 out, 2m squared plus 2m plus 1. Now you can see that I've got 2 times something, which will be even, plus 1, therefore it is odd. And afterwards then you want to finish with some sort of statement just to explain that. I'm not going to put it in here, but just something like the last one, but with 2 times anything plus 1 is odd in there. Now, for this one, prove that every odd number between 2 and 24 is either prime or the product of 2 primes. Now, the easiest way to do this is, let's list them. We want to do the exhaustive method. There's not too many, so it would be much easier to list them. 15, 17, and 23. Actually, let's fit 23 in down the bottom there, so that's the last one. So, first of all, we want to say, right, prime, 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 so there's all our prime ones. Now we want to find product of 2 primes for the ones that remain. So 3 times 3, therefore product of 2 primes. 3 times 5, and then 21 will be 3 times 7. And there we have it. Quickest and easiest way there. Now, with number 5, this is where we're starting. So remember to start by jotting this down on the side in pencil. It's what you're playing with to get you some sort of statement of fact to start with. So square both sides. And then expand. Take away 4pq. And then if we look here, we should be able to refactorize that. So this is now the place that we want to start, because this is a statement of fact. Anything squared is greater than or equal to 0. So very much like the example I did at the start of the video, this is where we want to start. So we want to consider p minus q squared. And we know that p minus q squared is greater than or equal to 0. Why? Because anything squared is greater than or equal to 0. Okay, you can put that in, I'm not going to bother this time, but it's now just a matter of going in reverse. So p squared is, p minus q all squared. When I expand it, it's going to give me p squared minus 2pq plus q squared. And then we obviously want to add 4pq. Now, with this final step here, this is where we're using this positive numbers part, because I cannot, sorry, I'm having a bit of a coughing fit then, so I cannot square root a negative number. So technically, you know, this obviously could in theory work for the square root side if both p and q were negative. But if they were both negative, then the left-hand side would be negative and this statement wouldn't be true. So we can say here, you know, p and q positive because the square root of a positive number is what you want. So you want to put that in there somewhere, because it's nice to say where you're using the condition from the question within your proof. Okay, and that is essentially all I need for part A. Now for part B, we just want to show that this is not true if they are both negative. So let p equal, let's go -1 and -4. Now I'm doing this because I'm picking two numbers that when they multiply together with this 4 that's going to give me a square number, just makes it a little bit easier when I'm demonstrating this. So now I can see that p plus q is equal to -1 minus 4, which is -5, and square root of 4pq is the square root of 4 times -1 times -4, which is the square root of 16, or 4. We can see that these two are not the same, so therefore this statement is incorrect or untrue. Okay, so always finish it with a sentence. I'm not going to fit it in here, but always finish it with a sentence. Hope you found today's video useful. If you did and you're new to the channel, or you've been here a while but you haven't subscribed yet, just think about subscribing. And if you spotted a mistake or you've got some questions about anything I've done in this video, just drop me a message in the comments and I'll get back to you as soon as I can. See you next time.